Hello everyone again, and welcome to this particular video where we're going to explore something quite interesting. We're going to focus on hybridized atomic orbitals. Now you might be wondering, what are those three names? We know atomic orbitals, of course, because they are coming from a specific atom which has different quantum numbers in terms of not only the orientation but also the shapes, where we have the s orbital, which is in this particular form, it's spherical. However, we have, for the purpose of the classes that you guys will be in, mainly the first year, you'll be exposed to the p orbitals. One is actually positioned on the x-axis. Pretty much the lobes, they are equal in size, but we're just going to ignore the scale right here. And then we have one on the y-axis, which is kind of in this particular direction right there. And then we have one on the z-axis, which is actually pointing upwards. So this color, that color right there, and this color, so that's positive and the other one is negative. So moving back to what we are actually talking about in this particular video, we are exploring what it means to be able to actually go from an atomic orbital and the reason why that is the case. So in here, we're going from atomic orbitals. We have the s, we have the p, in this case the direction is the x, the py, and we have the pz. These are all atomic orbitals, but for a compound to actually be created, you need to actually have the formation of bonds, and for the purpose of this, we actually need to be able to form covalent bonds. To form covalent bonds, atoms in the center, or the center atoms, they perform something quite incredible. In quantum mechanics, we actually have a particular wave function, which is a mathematical expression that tells us actually what is happening when the electron clouds in there are actually interacting, not only in terms of the atomic orbitals but their orientation. Like in this case, we're going to have a form of overlap in a way between the s orbital in the same energy level and the p orbitals in the same energy level. So in this case, what results in is that for our first case scenario, we're going to have the overlap of the s and p, which leads to the hybridization, which we just call hybrid. In this case, this leads to the formation of two sp orbitals. So in this case, we have one sp and the other sp orbital right there, because it comes from two atomic orbitals. So if you have n number of atomic orbitals, we should produce the same amount, which is n number of hybrid orbitals. So the next one is, for example, we have s overlapping with a px and with a py. What we have in this next case is the hybrid, which is actually having a different orientation compared to the other one that we did previously. So in here we have a sp2, 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 and those right there are actually having, each of them having the same energy created in that particular process. And then finally we have the last one, which is the overlapping of the s orbital, the p orbital on the x, the p orbital on the y, and the p orbital on the z, that results in the formation of our final one in the sp state, to be in this particular format, where we have one of the sp orbitals actually on the plane of this particular screen, and then we have one orbital that is pointing outside of this particular screen, and then we have another one that is actually on the plane of this particular screen, and then finally the sp3 orbital that is behind this particular screen. So this actually shows the three-dimensional look of not only this particular molecule that is going to be formed based on the geometry, but also the angle that is actually created. And based on this particular angle and geometry, and also the hybridization states, this is actually relatable to this chart that you should actually know. It's actually important to know that. So in this case, our first part is where n number of electron pairs is equal to 2. That means for electron pairs, we must have the combination of not only the lone pairs but also bonding pairs. So in this case, we just have sp because we have 2 atomic orbitals creating 2 hybrid orbitals, and the 2 hybrid orbitals will only create 2 bonds as the starting point with no lone pairs as indicated right there. So the next one is where we have sp2. That means that we have 1 s orbital and 2 p orbitals forming 3 sp2 orbitals. That means this 3 is actually shown by the number of bonds first, and then as you move from left to right, although they must have the same hybrid orbitals, which is sp2 hybridized, but the number of lone pairs increases from left to right as the number of bonding pairs decreases from left to right. And then when you get to number 4, in this case we must have 4 orbitals. To make 4 orbitals that are hybrid, we need s and all the 3 p orbitals. So we have sp3, and in this case the same thing is applicable in terms of increasing the number of lone pairs with decrease in the number of bonding pairs. That also causes, importantly, the bond angle to decrease. This is due to the fact that there is electron repulsion within the particular electron lone pairs that causes the bond angle to actually decrease right there. And then in here we go into sp3. Since we want to get to 5 electron pairs, which is what we have right here, we're missing 1 orbital. Where would the next orbital come from? Hey, the d orbital. So in this case we'll have the d orbital, and what happens is that as we move from left to right, the same thing is applicable. We have a change in the shape, but the geometry remains the same, and the orbitals hybridized remains the same. But in here we're having a decrease in the number of bonding pairs but an increase in the number of lone pairs, and the lone pairs are actually created first at the equatorial position first before focusing on the axial position. But that will come later when we get into the next one, which is sp3, and then we add a second d orbital, and this actually shows increase in the number of lone pairs with decrease in number of bonding pairs, but the hybridization on each of them remains the same. So an example of this is actually given a complex iron acetyl acetone, 3 of them, where you have this particular chemical formula, but then we're given the Lewis structure, which is great. I think for now we are asked to determine the molecular geometry, which is based on the VSEPR structure and the hybridization of that particular ACAC, which is given right here. So usually what I do is I create a little chart right there, where first I need to be able to highlight the carbons, and by highlighting the carbon I can just highlight this as carbon A, carbon B, carbon C, carbon D, carbon E, and in here we just have carbon. And then taking note of the assigned carbon, the next point is to be able to actually highlight the number of sigma bonds. So number of sigma bonds, I just put that right there. And then the next one is to be able, based on the number of sigma bonds, is to be able to take into consideration the number of lone pairs. So I'll just put number of lone pairs, which is LP in this case. And then based on the combination of the number of sigma bonds and number of lone pairs, I can then determine what the electron pair geometry is, that will then allow us to conclude what will be the hybridization of that particular carbon center right there. So for carbon A, we have carbon B, C, D, and E. So looking at carbon A, which is what we have right here, we have 4 bonds. In this case, the 4 bonds are all sigma bonds, and then we have a lone pair, which is 0. We don't have a lone pair at all. Now the electron pair geometry is, looking at this particular chart, we have this one right here, which actually has 4 bonds with 0 lone pairs, that actually tells us that it is tetrahedral, and it has a hybridization that is sp3 hybridized. So we just put tetrahedral, TH, that will be our tetrahedral short form, and then our hybridization is sp3. So that's about it for A, which is great. And then B is, since we have sigma bonds, which is 1, 2, 3, that means we have 3 sigma bonds, or you can just count the double bond as just on that particular area. So we just consider a double bond to be a single bond in this case. Always do that. Anytime you see a double bond in a specific particular area, that single bond is considered to be that double bond is considered to be a single bond. So this will have a lone pair that is the carbon to be 0. In this case, 3, 0 means that, looking at this chart, we are actually right here. That means that we have a trigonoplanar because it has 3 bonds but 0 lone pairs with sp2. So in here we have a trigonoplanar, and this has a sp2 hybridized state. And then for C, the same thing is applicable. We have 3 bonds with 0 lone pairs, and the electron pair geometry is trigonoplanar and sp2 hybridized. And then the d orbital, in this case here, the d carbon here has double bond, which is considered to be a single bond. And then we have 3 bonds in total in here. Number of lone pairs is, in this case, 0. We have a trigonoplanar and sp2 hybridized. And finally, E is the same thing as A, so we go with 4 bonds with no lone pair. That means it has a combination that is electron pair geometry to be tetrahedral. And then finally, the hybridization is considered to be sp3 hybridized. So in here we're able to answer the molecular geometry VSEPR structure, which is this right there, and the hybridization, which is those right there for each of the carbon atom. So that is incredible. And then the next one is, when you have 2 oxygens in the AC coordinated with iron, determine the geometry and the hybridization of the metal complex. So in here, since we have iron positioned right there, it means that this ion will somehow coordinate with the oxygens on both sides of our particular ACAC, and this will actually be pointing this way and this way pointing the other way. I'm just doing the shorthand version. Usually there is resonance happening right here that creates a form of a negative charge right there, and then this is the other one where now we have the oxygen on the other ACAC actually pointing towards you, and then we have the carbon actually forming with this other carbon, and this carbon is with this oxygen, and this time this oxygen is actually on the plane of this particular screen. We have our particular electron right there, which actually shows a resonance with the negative charge around that region. And then finally we have the last particular ACAC where the oxygen and the other oxygen actually is bonded right there to, or coordinated with, this particular ion. Thereby this actually shows a resonance around this region due to the double bond right there as shown right at the top. All the same, that's about it for this particular video. Please, I hope you're able to understand this. Please hit a comment down below. Let me hear your thoughts about the hybridization, and most importantly, noticing in here that this is actually known to be octahedral, because that this has ion has 6 bonds, and since it has 6 bonds, there is no lone pair on that particular ion. Thereby, as a result, we actually conclude that it not only is octahedral based on what we have right here at the top, but also we actually know that the hybridization on iron is that it has a sp3, but now it uses its 2d orbitals to actually enhance the formation of the 6 bonds, accommodating the 3 ACAC molecules. So stay smart and believe in yourselves.